We are on week 6 today, and so I thought we'll do a very short, very brief sum up of where we are. We will take last week, that is week 11, to sort of do an overhaul and wrap up on the course, but let's just see where we are, what have we accomplished so far. So, for most of the part, we have been studying this particular kind of an agent which is acting in a deterministic environment, and it's a single agent that is acting in the environment. Now, if we are in such a situation, the first thing that we did right early in the course is said, okay, let us create an atomic version of this agent which will think about the basic algorithms that can be used to solve any problem which is in a deterministic single agent scenario. We talked about uninformed search, we talked about heuristic search, informed search, we talked about local search. And then we went inside the state. And this was the leap from the atomic version of the problem to the knowledge representation component of AI, which is how can I represent different domains, and based on how I represent the different domains, what can I gain or lose. So the first knowledge representation language that we studied was constraint satisfaction, which had variables and values, and the goal was to find a satisfying assignment. We realized that the algorithm that we use to solve them is exactly the same. It's one of these algorithms like that first search. But because we are in a specific scenario where we have variables and values and all the solutions lie at the same depth and and so on and so forth, we could add specific knowledge about this particular representation. Like we could do inference, arc consistency, and forward checking. We could also use local search, by the way, that fits too. Second kind of representation was logic, and again with logic we could make new inferences either using mode exponents or using resolution, and then we have the problem solving equivalent of the satisfiability problem, and again we could model any problem as a satisfiability problem, any NP hard problem, any NP complete problem as a satisfiability problem, and solve that using the satisfiability solvers, which is what we are working on. Interestingly, you can go from SAT to constraint satisfaction, you can go from constraint satisfaction to SAT. The third in the same line, although I don't know whether Andre introduced it like this, the third in the same route that you studied is the strips language for classical planning. And there the idea was that we have an action, and that action can be applicable in a certain state and will change a part of the state. This is my representation. That's a natural representation for when I'm doing goal achievement in an environment which is changing by my actions. And so, for that kind of a representation where I have preconditions and effects, I could create heuristics. So the algorithm is heuristic search, A star, right? It's the standard algorithm for atomic agent, but we could do an automated heuristic which made use of this representation, and that was the planning graph heuristic. Again, the interesting thing is you can convert from classical planning to CSP, you can convert from classical planning to satisfiability. So these are all interchangeable, or not all interchangeable, but a lot of this is interchangeable representation. Yeah, actually you can go from satisfiability to classical planning also, although that will not be very useful. Then, the last thing that we have done so far is that we have gone away from a deterministic single agent scenario into a one person. Paul.
Probabilistic.
Have we already gone to probabilistic scenarios?
Oh, that's what you said right now.
Adversarial.
Yes. We have gone from deterministic single agent to deterministic adversarial, probabilistic adversarial.
Adversarial or indeterministic?
Deterministic adversarial. Why deterministic?
The best possible complete knowledge.
So when I say deterministic, what do I mean? I mean that my world is deterministic. If I move my bishop from this point to this point, the bishop moves from this point to this point. There is no uncertainty. Moreover, so let's talk about uncertainty in a minute, but the point is that everything is known to me and everything is completely, whatever I do has a completely deterministic consequence. That is the reason we call it a deterministic domain. And there, I don't know if Alan introduced it like this, but we did an atomic agent. So now we cannot use A star. Why can't we use A star?
We don't control every move.
We don't come exactly. So A star, depth first search and everything assumes that I am the only person changing the world. I, the agent, is the only thing, agent, force that can change anything in the world. That is true for, say, solitaire. That is true for, say, how do I take these blocks and convert it into this configuration of blocks or whatever it is. That is also true for your auctions problem that you worked on in the first assignment. You are the only agent. You got the bits, and now you are the only agent deciding, you are the only agent which figures out what to do. That was the assumption in all of this. However, that assumption is no longer true when we go into adversarial scenario, because after my move, there is another agent which is going to take their move, and that move I can't predict, and therefore I have to make sure I know what to do in all of the circumstances. So the atomic agent for that is Minimax. And then there is a full field that you can further study and add same kinds of intuitions, knowledge representation intuition, and so on. For example, one of the knowledge that we added in order to make this tractable is this knowledge of the evaluation function or the utility function. If we have to cut off the search, what do? We have to evaluate the leaf node that we have not been able to reach. So let's just create some evaluation function that tells me how good this particular state is. Where does this evaluation function come from? We'll see if we can get there towards the later part of the course. But for now, we assume that it was given to us, that was the utility function or the evaluation function. And then one could apply game-specific heuristics. And today, people are creating these knowledge representation languages for adversarial domains. So there is a competition called General Game Playing Competition. AI community likes competitions. SAT competition, computational auctions competition, which you also participated in, by the way, without realizing. And if some of you feel that your code is really cool, then you may really want to participate in the real competition. I'm not kidding. Similarly, we have general game playing competition, and the idea of this competition is the following. You don't know which game you're going to play. So you are going to create a general game player, and at the last minute or one day before, you will get various games that your same algorithm is supposed to play. They may be board games, they may be, I don't know what games it will be. The rules will be told to you in a formal language, like strips, but not exactly strips. It will have adversarial situations in some representation language, and you would have to make heuristics, utility functions, algorithms that will take that representation and play that game the next day and defeat every other agent. That's the goal of that competition. It's pretty awesome. But we are in early times as far as general game playing is concerned. So this is where we have been so far. And now, so also notice that I have characterized this as traditional AI, because these are the kinds of things people in AI used to do, started doing even in early 60s and so on. Now, they're going to take the leap from traditional AI into modern AI. And can you guess what's going to change? Yes, we are going to get rid of the determinism in everything. And we are going to get into uncertainty. And the reason this is important, as I have probably said over and over in the past, that world is not deterministic. A world at the level of abstraction that we can do anything computationally is not deterministic. And therefore, and deterministic scenarios are brittle. Logic is brittle. Logic cannot handle exceptions, or usual kinds of logic cannot handle exceptions. And there are exceptions to every rule, everywhere in the world. So how do we handle that? We handle that using some knowledge of uncertainty. And this is what we're going to do for at least the next 4 weeks. And then we'll see what to do in the 10th week. Okay. Now, uncertainty can come in many forms. Any guesses of what are the various forms uncertainty can come. Yes, Alan.
What an action is going to cost.
When an action is gonna
Cost.
what an action is going to cost. Yes.
No.
Exact knowledge of the environment around you.
The knowledge of the environment around you. So notice that there are two different things here. Actually, they are similar and different. So one thing is what an action is going to cost. Do I know this or do I not know this? That is one kind of uncertainty. Similar what Chris said. Do I know everything in my world, world, or do I not?
I mean cost, not cost. Like, what's going to cost? Sorry, like,
What occurs?
Yeah, like what's going to
Happens.
after you.
Right. That is the other kind of uncertainty. So first kind of uncertainty is I don't know.
Right.
Any game that you can think of where I don't know everything?
Do you like cards?
Yeah, bridge, for example. I don't know everything. It's partial information. It's a technical term for it. In chess, I know everything. Everything is right in front of me. There is no problem. Now, there is another kind of uncertainty which Alan originally talked about, but I didn't understand. That is the uncertainty of what happens after my actions. So Alan thought he would say something and I will understand it. But there is uncertainty in his actions. So he said something and I understood completely differently. What is that kind of uncertainty? That is the uncertainty in the domain itself. An example of a game where that kind of uncertainty happens?
Craps. Craps for
Yes, whenever you roll a die, for example. I don't know craps, but I think it's similar.
You roll dice and fail.
Exactly. So, and there are many examples like that. Whenever you deal cards, also that's something. So now, and the third uncertainty is the uncertainty due to multiple agents. So I am going to change the world, but my world may change due to some other agent, and how that's going to change, I don't have control over it. So there is some uncertainty. So this kind of uncertainty you have already, this kind of uncertainty which is in the other agent you have looked at a little bit. So what we are going to do is for today look at decision making, complete decision making today, but in the context of the uncertainty which is in the outcome of my action. Okay? And we'll also touch a little bit on when the uncertainty is in the knowledge of the world, depending upon time. So that's the goal for today. So let's start. And the topic that I'm going to start with, it's called decision theory. Okay. So what is decision theory? Decision theory is an analytical and systematic approach to the study of decision making. It's just it's actually, you already know decision theory. Let me argue the following. That you know what decision theory is, we're just going to give it a name today. So, what are good decisions based on? So good decisions are based on thinking, reasoning, figuring out the options, figuring out the data, figuring out my knowledge, and ideally employing some kind of a quantitative approach. That is what decision theory studies. Decision theory studies how do I quantitatively make the best possible decision. Whereas bad decisions may not be based on reasoning, may not consider all information available, and may not employ a quantitative approach. Now, here is a most important point. One of the most important points. A good decision may result in a bad outcome. And a bad decision may get you lucky and result in a good outcome. That doesn't mean that a good decision was bad or the bad decision good. This is actually the core of decision making in an AI, from an AI perspective. There is some information that you have today. Your best decision is based on your current information. Tomorrow, if you get new information which makes your current decision bad, that doesn't mean that the time you took that decision, it was the wrong decision. Does that make sense? How many times you choose an alternative and next year or a few months down the line we say, damn, if I had chosen that other alternative, 3 months back. Has any of you been in that situation? Here is the main mantra. You did not take the wrong decision. At least, given what I've told you, you did not take the wrong decision. Why? Because you don't know what's going to happen to you 3 months in the future. That's the most important thing. The best you know is the probability distribution. Now, if you make a computation mistake in figuring out the probability distribution of what's going to happen to you 3 months in advance, then yes, you made a mistake. But you cannot compare a life that you led for 3 months or a year versus a life that you now believe you would have led if you had taken another decision then. Just wrong. Doesn't make sense. So decision theory is really applicable in practice, in real life. It gives you a basic framework how to figure out the right decision. And then if you go down an unexpected outcome, bad things happen to you, you should feel proud that you still did the right thing, you took the right decision, it didn't work out, sure, there is a luck factor involved. If you disagree with me, please talk to me. I believe very strongly about this.
So was it a good decision to buy Facebook stocks on the day of its IPO?
That's a good question. So it depends on your probability distribution of what you think is going to happen and how you came up with this probability distribution. So in some sense what you're getting at is often we are not able to come to a probability distribution of the future. That is where everything moves to. So that will be reinforcement learning. We'll talk about it in the 9th week. But for now, there's one and only way of doing things if we know the probabilities, if we know our model. So let's assume that what we know is that we have full knowledge of the world, or to some extent, and what is uncertain is the outcomes of the actions. Okay, so these would be the steps. We'll go through this rather fast because this is not very complicated. So these are the steps. We'll list the possible alternatives, we'll identify the potential possible outcomes, we'll list the reward or profit in each possibility, and we'll apply one of the models to figure out what's the best decision. So here is my example. The Thompson lumber company. So after today you would know how to manufacture or how to do wood manufacturing. So backyard storage sheds. So Thompson Lumber Company must decide whether or not to expand its product line by manufacturing and marketing a new product, backyard storage sheds. So these are my possible actions. I could construct a large plant to manufacture the sheds, or I could construct a small plant to manufacture the sheds, or I can do nothing. Be like a lazy man having fun in life, not do anything. Okay. Then what we are going to do is identify the potential outcomes. States of nature, that's also a word sometimes used. Because it's a state of nature, it's something we don't have control on, nature has control on. So an outcome for which the decision maker has no control, lottery, coin toss, whatever, whether it will rain today would be more or less true, but for the fact that we are in Seattle, so we can't really say it's a state of nature, we know what's going to happen more or less. So, now the market for the storage shed could be favorable or unfavorable. That means we may have high demand or low demand, something we don't have much control on. But we don't know right now which scenario we are in. Now, depending upon what we do and depending upon what the state of nature is, we may get bigger profit, smaller profit, loss or something. So if we produce a large plant and the market is favorable, we can make a lot of profit, so we make $200,000. If we make a small plant, we are not able to meet all the demand, but we can still make $100K profit. If however we make no plant, we make no profit, so life's good, but we don't win. On the other hand, if we have an unfavorable market, the large plant which produces a loss of minus 180K, a small plant produces a loss of 20K, and no plant, no profit, no loss. So how many of you are going to build a large plant? How many of you are going to build a small plant? How many of you are not going to do anything? That can't be right. I guess you are already not doing anything by not raising the hand. Sounds good. Yes, question.
So the cost of each possibility is kind of hidden in the net loss.
In the so it's a net. But if you had a cost, then you can add a subtract. All right. So at the level of specification that I have given you, it's really hard to say what we should do, but let's still think about it. But in order to think about it, we'll create this kind of a table. So the table says on the left we have actions, on the right we have the possible outcomes, and in the middle we have the rewards. So for example, my actions are large plant, small plant, no plant. Outcomes are favorable market, unfavorable market, and these are the payoffs or the rewards or the profits or whatever you want to say for all of these scenarios. Okay. Now, what we'll talk about in the next 15 minutes is various kinds of models. So here is, we haven't specified anything, right? So you don't know anything. So that is the uncertainty, and it's called the non-deterministic uncertainty. So in other words, I am not giving you the probability distribution of any kind. I'm only telling you that either it can be favorable or it can be unfavorable. Now you figure out what to do. This is the specification that I've given you. If I only give this much specification, it's called non-deterministic uncertainty or disjunctive uncertainty, because it's favorable or unfavorable. Now you understand disjunction very well because you are working on SAT clauses, so that's the same term. Yes.
Does it mean like probability half and half?
No, it does not mean probability half and half. It means unspecific. We don't know. So if we don't know, we can't assume half and half. So let's work on non-deterministic uncertainty. So there can be multiple kinds of agents. Right? One agent may be most risk prone. Somebody who believes that I can go for the gold. I want to maximize my profit, and that is the only thing I want to do. If I really wanted to maximize my profit, what would I do? Exactly. So I will build a large plant, and that's the, in the strategy, it's called Maximax strategy, which means take the max of each row, which is the max, the profit that you can get for each action, and then take max in this column, and that would be the total max that you can get. That is the large plant. This is also the most risk prone agent because it may often make the highest losses. What is an equivalent strategy, like the complementary strategy to Maximax? Minimax. Minimin. Minimin. Like take the worst that can happen to me in each action and then take the worst action from those?
Take the least bad action.
Least bad action, so it would be?
No plan.
Yes. Come on. So basically it's the best of the worst. Why would I take worst of the worst? I'm choosing to have my life most miserable as possible. Of course not, right? So I'm going to choose my life which is least miserable. So I'll figure out how much misery am I going to get in each of those and then take the best of that. So the best would be the max. So in other words, the large plant, what's the worst that can happen to me? Loss of 180. Small plant, what the worst that can happen to me? Loss of 20. And no plant, no loss. So what was I would take the maximum in the column, which would be $0. So if I was very risk averse, if I really didn't want to make any losses, then the best strategy is to have fun, be a saint. Which is fine. People do that. So we are all different people. Some people want to take more chances, some people do not. So if people who do not want to take any chance, most often than not, they will not do anything in life. That's what this particular example is showing. At least they will not do anything in life. They wanted to build backyard storage ships. Okay. Then here is Abhishek's suggestion, which is I really don't know what's happening. I can't go for the best or the worst because neither the best nor the worst might happen. So what should I do? Well, let's assume that the best and the worst can happen with probability 50% each. And that's called the equal likelihood criterion. So you compute the average reward assuming that either the best happens or the worst happens with probability half each. So here we have only two options, so the best and worst are easy. So we just take 0.5 probability 200 plus 0.5 probability minus 180, we get an average of 10. Similarly, for small, we get 40. For no plant, we get 0. So, in this criterion, if you assume that the best and the worst can happen with equal probability in my life, then you get small plant. Many of you had chosen small plants. You guys seem to be reasonably balanced in your optimism and pessimism. Great. Another criterion is called Criterion of Realism. So it says that I am optimistic with a factor 0.8. Let's say I'm optimistic with a factor 0.2. So anything like that. So I'll take my optimism factor or realism factor times the rho maximum plus 1 minus alpha times the rho minimum and construct an average value which is more realistic. So if my coefficient of realism is 0.8, that means I am 80% optimistic in life, then my numbers will be 124, 76 and 0, and then I will choose the large.
How do you compute that alpha?
You don't compute that alpha, this is who you are. You know your alpha. Again, in some sense what we are doing is that because it's an underspecified problem, we are just studying the various possibilities of how to make a decision based on a pre-specified model.
So all of the options were just values of alpha. So 0 means max.
Yeah, of
1
course.
means
0 means completely pessimistic person, 1 means completely optimistic person, and 0.5, yeah. No, I think equally likelihood is different because equally likelihood computes the average reward for each alternative. So I made a mistake here. So in equal likelihood criterion, I assume that all the possible states of nature are equal probable. So if there are 3 states of nature, then I have 1/3, 1/3 each probability, which is different from criterion of realism, which only computes the rho maximum and the rho minimum. Subtle point. Last, this is the last model, and then we'll get to the more fun stuff. The last model is called Minimax Regret. Okay, so this is slightly tricky. I mean, not tricky, slightly sort of reverse. So it says, what is regret? So regret is the difference between the best I could have done if I knew the future minus what I actually got. So it is how much am I going to feel bad? That's the point. Right? And I will pick the one which minimizes the max regret. So this is the max regret means this is the worst that I can feel bad, and minimizing that is the best from that alternative. Let's do an example and that will become much clearer. So the point is, if I knew the future, how much I'm going to regret my decision. Okay, that's the model. So let's think about this. If I decided to do the large plant and the market turned out to be favorable, how much am I going to regret? Minus what? Minus 100,000.
Why would
So
you
if
do
you
If
it?
I build a large
Your
plant,
regret would be negative, so you are excited that you got 100,000.
no. So regret is the best I could have gotten and what I get.
So 0.
Zero, exactly. So I could have gotten 200 and I get 200, so my regret is. So in order to make these computations, the first thing you do is you figure out what is the best payoff if I was in the favorable case. So the best payoff is 200. The best payoff in unfavorable case is 0. And then, so if I'm in the large plant setting, then my regret is going to be 0. If I'm in the small plant setting, however, what's my regret? Exactly. If I don't do anything, what's my regret? Right. Similarly, what's the best payoff for unfavorable?
0.
What is the regret for large plant? 385.
Well, because you could have paid 200 instead you.
No. See, the 200 is no longer possible because now I'm in the unfavorable state of nature. Right? Similarly, in the small plant, my regret is, and in no plant, my regret is. Okay. Now, should I minimize my regret or maximize my regret?
Minimize.
But should I minimize my max regret or minimize my min regret? Max regret. So I want to take an action which gives me, so for one action, the worst that can happen to me comes in this particular column. So the worst that can happen to me in large plant is who believes that the worst that can happen to me is 0? Right? 180. Similarly, 100 is the worst that can happen to me in the small plant setting, and in the no plant setting, the worst that can happen to me is 200. So if I was to minimize my max regret, I would take small plant. These are the regrets. So I will pick the one that minimizes my regret, and that's 100. Yes, we need that. Why is 180 the first column of the max? This one. So it says that if I chose to do large plant, then in one case I will have regret 0, but in other case I will have the regret 180. Because I am making a decision now, but I don't know what's going to happen to me. The worst that can happen to me is 180. But then I'll pick the action where my worst is least. That's the other model. It's called Minimax Regret. Yes, Samir.
So what is the motivation for Minimax Regret? Sounds like a very unhealthy way of making a decision. It's exactly what you couldn't do.
Really? Why is it unhealthy?
Psychology.
You always second guess yourself. Obviously for human beings, kind of. But why is it good for an agent? Is it a better model?
It's not a better model. No, none of these models are better models. These are just modeling different ways of thinking about the problem. One way of thinking about the problem is I want to get the best I can get. One way of thinking about the problem is I want to get the worst that I want to reduce the worst that I could get into. Another way of thinking about it is that I want to feel least bad, a year down the line when I knew what I could have got. So I want to minimize my difference from the optimal that I could have got.
So one motivation comes from like machine learning where like you're trying to do predictions. So suppose you're predicting stock prices for somebody, right? And you're competing with other people who are predicting the same thing, right? So you want to basically be as close to the best as possible because that's what's going to get you business.
So the regret is very commonly used in reinforcement learning, which is where your probably explanation is coming from, which is that I want to learn about the model and I am taking some decisions, and later, after 100 tries or 200 tries, I will see how much I have learned, and then I will think about, is this learning good enough? And the learning is good enough when the best I could have gotten after having known the future, and how much I'm getting now, that difference is very less. And I guess that's where DJ's interpretation is coming from. I think it's a model. Okay, so this is what we have figured out. If it's a completely optimistic agent, build a large plant. Pessimistic, do nothing. Somebody more realistic, either somewhere between small and large. But now let's come to the more fun stuff, which is what happens if I have probabilistic uncertainty. And now I'm going to believe that I know the probability of what's going to happen. So therefore, in that situation, if I know the probability of what could happen, so say the small plant could happen with probability 0.5, and the large plant could also happen with probability 0.5, and I know this, then what I could do is I could do an expectation. I could do an expected value computation, and that will give me a model for decision making in probabilistic scenarios. So that will be maximization of the expected reward. An equivalent criterion could be minimization of the expected regret. In this particular scenario, however, the great thing is that maximizing expected reward and minimizing expected regret comes to exactly the same conclusion. So at this point, these models are really the same. Yes?
For every P?
Yes. You should prove this at home if you're interested. Okay? So, expected reward is rather straightforward. You take probability of the outcome times the reward in that outcome, and we'll call this Q. Also called expected monetary value, expected value in various literatures. So again, we have done this computation. So if we assume that both of these are equally probable, then my expected monetary value, or Q, of the large plant is half times 200 minus half times 180, which is 10. This is 40, this is 0. And so I get that my expected value is maximized by taking small part, by building a small part. Yes,
Is the reason that that this is the same whether we are minimizing regrets or maximizing, because we only have two outcomes of two prospective outcomes, like favorable and unfavorable, or is it?
you can have as many outcomes as possible. Now, this is the most interesting question that I'm going to ask. Yes. Hello?
For the previous slide, how that one is different from the realism slide that you saw?
Right, because
In one case, it is our own way of making decision versus the actual some more world data that we had.
precisely, you hit it right. So where in the criterion of realism model, we said that I have some notion of optimism. That is my own parameter. Whereas here, this probability of what's going to happen is given to me, because that's the world that is the other. Tyson, right? You guys sit together. Very
So
happy.
with the criteria of reality, I think you said that it's only the
Maximum and the minimum, because
with this, would it be every
all alternatives, precisely. Great.
Why wouldn't you just do some sort of Monte Carlo simulation?
For what?
Well, it says you got a probability distribution function which is changing the values of your outcome. Why not just run a simulation and run a Monte Carlo simulation and take a look at, because you've got some PDF then associated with your output value as well.
So we already know how to do this. Why do we need to do Monte Carlo? We can actually
Well,
compute
because
this
is the
optimally.
simplest possible.
So are you
example.
saying that computing the expected value might get really tricky if you have a more complicated network?
Oh yeah, I mean,
Sure, yeah. So we will talk about a lot of this in the next 2 weeks. We'll
Okay.
talk about Bayesian networks and simulations and everything. But for the purposes of this, we're just abstracting away and saying that we know the probability of each outcome, we know all the outcomes, we know all the payoffs, so we can just compute the expected value without thinking too much. Okay, so now I'm going to add the uncertainty in my knowledge, and I'm going to ask you the following question. Suppose I could hire an economist who claims that he or she could analyze the economy and tell me exactly what is going to happen, whether it will be favorable or unfavorable. How much should I pay this economist? Okay, so this is the interesting question for this lecture. It is called the expected value of perfect information. Why perfect information? Because this economist is saying that they will tell me exactly what's going to happen. So I'm figuring out the value of perfect information. So the question we are asking is, how valuable is this information for me?
Depends on how much you trust that person.
Yes, let's assume we trust them completely. So how many of your economists or have studied economics? Okay. So we will not make jokes on economists. But let's suppose we trust Dan. So he's a really nice guy, he can do his best job, and he has some sixth sense. So after all of this, he's going to exactly tell us what is going to happen in the future. Hello.
But if you pay him and they say it's not gonna go well, you're losing all that money, because you know you won't.
That is true. At the same time, I could have lost much more by
Exactly.
picking an action and figuring out later that it's an unfavorable. So it's okay to lose something upfront and save a lot of money in the future, as opposed to, right? Yes.
How much money will you be making with this economics compared to people who don't have one? What's your profit?
Exactly. So how do we compute that?
Or how much are those economists paying?
How much are those?
You won't pay more than the going rate.
Yeah. Yeah, that's a good question. So,
Or maybe you will.
this is the model to figure out if their going rate is too much,
Right.
it's more than what you should be paying them, then don't ask for that information. So, we are going to ask this question, and any guesses by the way? Yes.
You take what your guess would have been, and you take what their, for each outcome, each world state, you take what your guess would have been and what the best thing to do in that outcome would be, and then you need some way of figuring out the probability.
No, you know the probabilities, that's the good news.
Okay.
So you are sort of hitting it right, and I think somebody else was also hitting it right, I think Trisha. So the point is, there is some expected value that I can get today without knowing this information. Let us calculate the expected value that I will get tomorrow after knowing this information. And let's see the difference. And that difference is the maximum I should pay. I could end up paying less, but I shouldn't be paying more than that, for sure. So, in order to compute this, we already know what is the expected value. The expected value is 40,000. So the only thing we need to compute is what will be the expected value tomorrow after knowing this information, and we call this expected value with perfect information. It's different from expected value of information. It is expected value with perfect information. It says the expected or average return if we have perfect information about the future. So how do we compute this? Let's think about it. It's actually not very hard. So if my perfect information comes out to be favorable, what would I do? How much will I make? If my perfect information comes out to be unfavorable, what would I do? How much will I make? 10. So this is what I'm going to do when I have favorable. I will make profit of 200k. And this is what I'm going to do if I am unfavorable and I'm going to make profit of 0k. Give me 1 minute. What is the expected? So this is the value of with perfect information if I am favorable. This is the value with perfect information if I am unfavorable. What is my expected value with perfect information? 100k. Sunny, you had a question.
So the economist is not telling you the precise probability, they're telling you what is actually going to happen.
Precisely. But the economist can come back and tell me, you know, I'm 90% sure it is unfavorable, and then I will be able to. I mean, even if they're giving me 90-10 split, I can get this into computation somehow. It's not very hard. If once you figure out the high-level principle, then these computations can be easy. But let us suppose that for now, economist tells me that I'll tell you perfectly with probability 1, like certainty what's going to happen. This is what we're computing. That's why we call it expected value with perfect information. So this is the expected value with perfect information. What was expected value without any information?
40K.
So the maximum amount I should be paying the economist is?
I think it's got to be less than that because
Maximum, as I said, maximum amount.
Yeah, but you didn't calculate the cost of you didn't calculate the cost of your expert in your expected values. So put his number back in, and you'll get something
Say it
different.
again.
Well, because he cost you money. So if you paid him, you didn't make 200,000. You made 200,000 less what you paid him.
That's why we're looking at the difference between what we would make on our own and what we would make with the expert and saying,
Yeah, it's
that
gotta be-
difference is our cap.
But what you should
So
actually
if
pay
we
is got to
actually-
be less than 60
so-
because you spent money on it.
So you're right. So if we actually pay 60k to the economist, we make nothing at the end of the day, even in expectation. So I think that's your point, and I agree. So we should pay less than that. Maybe we should reduce our profit, but this is the maximum we should be paying.
So, to Alan's point is, what if we add the computation before we add his profit before we actually make the decision or take the
So
expected
we
value?
could do that. So we could say that I want to at least make 20k after all of this exercise. So Is that right though?
Yeah, the expected value, oh.
No. I think we're missing it. So today we can make about 40K in expectation. If we pay 60, then after this information we can make 100K in expectation. So we are really not losing money. Of course, by having this information, we are not making additional money, right? Because we are still making 40K because we paid this guy 60K. So we could pay them less, or we may want to say that by having this information, I want to increase my profits by 20K. So the maximum I will be willing to pay this guy would be 40K, right? Something like that. Yes.
If you go back to the previous slide, where you have you multiply each by the probability, those are the same probabilities that we had when we calculated the expected value.
Yes. Okay. Yeah. This is what I already know about the world.
How is this number useful? The 16. How is it useful?
It is exactly answering the question of how much the information is valuable to me. So there's a bigger principle. The principle is by not knowing something, I may lose monetary value. So I may be willing to pay money in order to get information. So it's like an information gathering action. That I'm paying this economist to get more information that allows me to make the best decisions. I should pay less than 60K. By paying 60K, I do not increase my total profits, or expected profits. By paying less than 60K, I actually increase my expected profits. Assuming that I completely trust the economics, I may want to discount it further if I believe that this economist is not going to give me perfect information, this economist is only going to give me imperfect.
How do you actually include that probability? Because most likely economists will come back with a probability.
Right. So if we believe, if the economist, say if I trust the economist to 90%. So if
I'm
I
not
say,
saying that. I trust the economist fully, but he says 90% it's favorable and 10% is unfavorable.
right. So if I knew ahead of time that the economist is going to give me a 90-10 split, then I can factor that in my computation. So instead of taking 200, I will discount this 200 and say it will be 0.9 times 200 plus 0.1 times minus 180. But you have to think about this. So let's not go too deep into this. You go back and think about this problem. You should first understand the basic issue, which is if the economist is giving me a 1-0 split, if the economist is saying that I know 100% that it's going to be unfavorable, or I know 100% it's going to be favorable, how much do I trust that? How much do I value that information? That's the computation we have currently done. Now if I know that the economist is going to give me a slightly different split, you should go back and think, how will I capture it? It should be very straightforward. Sean.
Nope, Andrew.
Sean, this is Sean.
Close.
Yes.
But then that wouldn't be perfect information if it was a 90
Yeah,
split,
yeah.
right?
The word will change, but the computation will be straightforward, yes.
Since we have the information from economists, right now we are assuming that this is the perfect information, why we are still factoring in the probability into our model?
You tell me. That's a great question. This is a question that you should all think. So, this is the value with perfect information. Why do we have a 0.5 here?
Because we don't know what the economists will tell us.
Exactly. We are deciding now what will be the value with perfect information. Right? He could come back and say favorable. He could come back and say unfavorable. So therefore, I have to take expected value with perfect information. How is the expectation coming from? Well, the probability distribution that I have today, which is 50-50.
Well, that's actually the value not only of the information, but it's the value of the information plus whatever action we take on that information.
Yes.
Which is why you shouldn't give the economists all of the money for that value, because part of the value is you building a plant and making a profit on it.
No, but we are already subtracting this later. So this is not what we pay the economist. This is what we maximum pay.
Yeah, I mean the value, the information plus whatever action we take is 60,000. So then you can give a cut on that to the economist.
So value plus whatever action we take after we get from the economist, their answer is 100. Whatever value we get without getting anything from the economist is 40. So this is the money that we have at our hands that we can divide however way we want. Some part of it can go to the economist, some part of it stays with us. That's
So we're saying with 0.5 probability, So let's not make it 0.5, that it's a very special case. Let's make it 0.8 and 0.2. So we are saying because it's 0.8 favorable, we are likely that with 0.8 probability the economist is going to say this.
Yes. So if our uncertainty a priori is very less, then the economist's additional knowledge that the economist is giving is less. If we know with more certainty what's going to happen in future, then whatever economist can add to it is relatively less. Okay, so you guys should keep thinking about this if you are already confused. But I want to finish with a fun point. So far we have sort of assumed that expected value is the right thing to do. But is it the right thing to do? Is expectation what we often want in life? So here are a couple of games for you to play. Suppose you could play this only once. You could play lottery 1, which gives you nothing. And you could play lottery 2, which with 0.5 probability gives you $100, and with 0.5 probability takes $100 from you. How many of you will play the lottery 1? And how many of you will play lottery 2? And what is the expected value of lottery 2?
0.
And for 1? 0. So, clearly there is something happening here, because a part of you feel this is better, a part of you feel this is better, but both have the same expected values.
Well, you said exactly once.
Yeah, exactly. For now. Makes life easy. So, therefore, expected value may not be the right metric in life. I would leave you with only this, by the way, but let's play some other games. So, exactly. So, lottery 1 always gives you $100. You can play it only once. Lottery 2 gives you $10,000, probability 0.01, and nothing with probability 0.9. How many of you will choose lottery 1? How many of you will choose lottery 2? Actually, ideally I would have hoped to see more of a
Drop to 0, then the answer will be
okay, let's what is this one? Okay, let's talk about this. This is even more fun. Now how many of you are going to take lottery 1? And how many of you are going to take lottery 2? Interesting. How about this? So you guys actually are probably the most what should I say? You think alike in some sense, I feel. Because here I would expect a much more division of the class. Because for most people, $100 is not as valuable as the probability of getting a $10,000, even if it's a small probability. Yes, you had.
Yeah, that's what I'm saying. Like, it's worth the same for all of us. Like, that kind of money, $100 is almost worth the same to all of us.
No, but I've done this kind of an experiment in the previous classes. Which
I was thinking, there's chances I will get something. It's very likely I will get nothing.
Right. So anyway, so the point is that value of money is not how much money that is. In sometimes, by the way, anybody who's going to take lottery 2 here? In the past, I have had a student who raised his hand with lottery 2. So how do we model this, right? So value of money, so we use the word utility of money for this, and it's studied in utility theory, which says that there are different kinds of agents. Again, these agents are of different natures, right? So some agents will be much more risk-averse, which means that if they have to pay a little bit amount of money, then it will have a larger negative utility. Some people are more risk-prone, which is exactly the opposite. So we can still use the expected utility criterion, but on top of the utilities. So this is a risk-averse agent. It says that as my money becomes negative, my utility becomes extremely negative very quickly. But the incremental value of an additional $1 million is not too much. Right? And that's probably, I believe that it's true for many of us, more or less. That if I make $1 million, then the next $1 million may not be as exciting for me, at least looking at it, thinking about it today. I don't know what happens when I make my million. So this is the, on the other hand, the risk-prone agent, which says if I can get more money, that's even more valuable, right? And if I'm losing money, who cares? So this must be true for like the multi-millionaire people, I'm guessing. And then this is what we have been optimizing so far. An expected value, which is where the value is itself, the money value is the money itself. So utility grows linearly. So in the future, we will still stick with expected value under the caveat that if you have an additional utility of money, then you can just substitute that and all the computations work. Now there are other models also which often say that I want to reduce the worst that can happen to me and things like that. Those can also be